Hi there. So today we're going to go over DeMoivres theorem and an application of it. Okay, so first let's just state the theorem and then we'll do a quick proof. Okay, so the theorem says that if we have n being a natural number, then cos x plus r sin x to the power n is equal to cos nx plus r sin nx. Okay, so this n from the exponent here goes into the argument for cosine and sine. Okay, so the proof is very simple. We just need to use Euler's formula that we looked at last time. Okay, so remember that e to the ix can be written as cos x plus r sin x. Okay, that was Euler's formula that we saw. Now on the left-hand side here, we have cos x plus r sin x to the nth power, but we know that cos x plus r sin x is e to the ix. So we can say on the left-hand side, that's e to the ix to the nth power. Okay. Now this n we can multiply inside, okay, using our exponential rules. So this becomes e to the I nx, just multiplying that in. But again, if we use Euler's formula on this, this is going to be cos nx plus r sin nx, okay, for the right-hand side. And for the left-hand side, we can just expand this e to the ix. So that's going to be cos x plus r sin x, that's e to the ix, and it's still raised to the nth power. Okay, so that's a quick proof of the theorem. Okay, so why is this useful? What applications can we get from it? Well, what we're going to be looking at is taking a trig function like sine 3x, something like that, where we've got this 3 attached to the x, and we're going to write it in terms of only sine x and cos x raised to certain powers. Okay, so this is going to be equal to a polynomial in sine x and cosine x. Okay, so that's 3x we replace with just x, but to do that, we are going to have to write it as a polynomial in terms of those variables sine x and cosine x. Okay, so how do we do that? Well, we're going to use this theorem here because we see on the right-hand side, we've got this here, cos nx sine nx. So in our case here, we just replace n with 3. Okay, that gives us the right-hand side, or one part of the right-hand side. We're going to expand out the left-hand side, and that's going to give us the polynomial that we're looking for. Okay, so we want sine of 3x, that's the goal. But let's consider this full expression with sine and cosine. Okay, so we know that cosine 3x plus r sine 3x, we see that this imaginary part, that's the part we're looking for, is equal to, and then we just use the left-hand side here. This is equal to cos x plus r sine x cubed. So the 3 from the 3x now becomes the exponent 3. Okay. Now notice that on the left-hand side, this imaginary part is what we want. Okay, because sine 3x, that's what we're looking for. That's the imaginary part. If we then find the imaginary part on the right-hand side, that will give us the expression for sine 3x. If we find the real part of the right-hand side, then that gives us the expression for cos 3x. So we end up getting 2 for 1. Okay, but we're only interested in the sine 3x in this case. Okay, so what we can do now is expand this right-hand side using the binomial theorem. So the right-hand side is a binomial, we can expand it out. So to get the coefficients for that expansion, remember those are the n choose k coefficients in that sum. We can just use Pascal's triangle. So the exponent is 3. So we're going to have 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. That gives us the coefficients. Okay, so it's a quick way of finding what those are. So this is going to be equal to, the first coefficient is 1, so it's going to be cos cubed x, plus the next coefficient is 3, so 3 cos squared x r sine x. The next coefficient is 3, so we're going to have 3 cos x r sine x, all of that squared. And the last coefficient is 1, so we're going to have r sine x cubed. Okay, so that's just expanding it out. Now we've got this r squared and the r cubed, so we can simplify that. So this is going to be cos 3x plus, we can take the r to the front. So we have r 3 cos squared x sine x. R squared is going to be minus 1, so minus 3 cos x sine squared x. And then r cubed, that's going to be minus r. So we're going to have minus r sine cubed x. Okay, good. Now, remember what I said earlier. On the left-hand side, we've got the real part corresponding to cos, the imaginary part corresponding to sine. We're only interested in the imaginary part because we're looking for sine 3x. So that means on the right-hand side, we need to look for the imaginary part. So let's collect the imaginary terms to one side and the real terms to another side. So for the real part, we're going to have cos cubed x minus 3 cos x sine squared x. That's the real part. And the imaginary part is plus r 3 cos squared x sine x minus sine cubed x. Okay, so let's just highlight that. So let's say the green part is the real part, the blue part's the imaginary part. We can do the same thing for the right-hand side. So the green part over here, that's the real part. And the imaginary part, we want that to be blue. So now we can just match them. Okay, because remember, if two complex numbers are equal, then the real parts are equal and the imaginary parts are equal. So from this, we get that cos 3x is equal to cos cubed x minus 3 cos x sine squared x. Okay, we're not looking for that, but we do get it for free, so we can write that down. And the part that we were looking for, sine 3x is equal to 3 cos squared x times sine x minus sine cubed x. Okay, so we see that it's polynomial in cos x and sine x. Okay, so on the right-hand side, we don't have any 3x terms. It's just in terms of x. Okay, but that's the one that we were looking for, so let's put that in a box. Okay, so we have an expression for sine 3x with only x being the argument for cos x or sine x. Okay, so it's not too difficult. All we need to do is remember this DeMoivres theorem, where the left-hand side is going to be cos nx plus r sine nx, or some value of n that's given. On the right-hand side, we've got the binomial, where the exponent is n. Again, that's given. So we expand out the binomial, and we look at the real and imaginary parts. We group that together. And then depending on if we're looking for cos nx or sine nx, we pick the appropriate part. So if we're looking for cos nx, we would take the real part of the right-hand side. If we're looking for sine nx, we would take the imaginary part of the right-hand side. Okay, so here we were looking for sine nx, so we took the imaginary part, And we've got that in the box there. Okay, let's have a look at another example. Okay, so let's say we have cos 4x, we want to find that. Okay, so same thing as before. Instead of finding cos 4x directly, instead let's look at cos 4x plus r sine 4x. So we add this extra part on, but using DeMoivres theorem, we know that we can write this full thing as cos x plus r sine x, and this 4 we can take out and put it as the exponent. Okay, so now we just need to expand this right-hand side using the binomial theorem, get the real part since we're interested in cos, and that's going to be our final answer. Okay, so now since this binomial is fourth order, we've got 4 over here. Again, we can use Pascal's triangle to find the fourth row. Okay, that'll give us the coefficients. So we have 1, 1, 1, 1, 2, 1, so that's for squaring. 1, 3, 3, 1, that's if we are cubing. And if it's to the power 4, we're going to have 1, 4, 6, 4, 1. We can stop there. That's what we needed. Okay, so let's expand this out. So we're going to get cos 4x plus 4 times cos cubed x r sine x plus 6 times cos squared x r sine x squared plus 4 again. Now we're going to have cos x r sine x cubed, and then last term, the coefficient being 1, so we're going to have r sine x to the 4. Okay, so that's all the terms in the binomial expansion. Let's simplify the r squared, the r cubed, and the r to the 4. And then we can collect the real parts and imaginary parts, and then get our final answer. Okay, so this is going to be equal to cos 4x plus, we can take the r to the front, so it's going to be r 4 cos cubed x sine x, that's just by itself, plus, it won't be plus, sorry. So we've got this r squared, that's going to make it a minus. So in fact, this is minus 6 cos squared x sine squared x. Okay, and then r cubed, that's the same thing as r squared times r, but r squared is minus 1, so we're going to have minus r. So it will be minus r 4 cos x, and then the sine cubed. Plus, and then r to the 4 is the same thing as r squared times r squared, but r squared is minus 1, so we have minus 1 times minus 1, which is just plus 1, so that's just sine to the 4x. Okay, now again, let's group the real parts and the imaginary parts together. So let's look at all the real parts. So that's going to be cos to the 4x. The next term is r times 4, so on, so that's imaginary. Then we're going to have minus 6 cos squared x sine squared x. The next term, that's imaginary. The next term, that's real. So plus sine 4x. Okay, and then we can have plus r and then all the imaginary parts. So 4 cos cubed x sine x. Okay, cos cubed x sine x. And then minus 4 cos x sine cubed x. Okay, so we've got the real part. Let's put that in green. So the real part on the left-hand side was cos 4x, and we've got the real part on the right-hand side. The imaginary part on the left-hand side, that's r sine 4x. The imaginary part on the right-hand side, that's going to be all of this here in blue. Okay, so now we can just match the sides. So cos 4x, that's in green. So cos 4x, that's going to be equal to cos to the 4x minus 6 cos squared x sine squared x plus sine to the 4x. Okay, so that's our final answer. That's what we wanted. Okay, so you can just leave it like that. But like I said before, we do get 2 for 1. So we could write sine 4x. It's not needed because it wasn't asked, but we can write it as sine 4x is equal to 4 cos cubed x sine x minus 4 cos x sine cubed x. Okay, so that's just a bonus that we get. Okay, so let's do one more, but I'm going to leave that for homework. Find the expansion of sine 5x. Okay, so same thing as before. Instead of having the argument being 5x, instead write this as a polynomial where the argument of the trig functions is just x, like we had over here. Okay, so that's going to be homework for today. Okay, so if you have any questions about DeMoivres theorem, the proof or the applications that we've gone through, please just send me an email or you can post a question on the WhatsApp group. Okay, remember the tutors are also available, so you can ask them for help as well for any of these homework problems or any questions in general that you might have. Okay, so in the next lecture, we're going to be going through complex functions. So that is a function that takes in a complex number as the argument and then produces a complex number. So it's going to be f going from the complex numbers to the complex numbers. And we're going to look at some purely complex functions. And we're going to also look at how we can extend existing functions from the real numbers to the real numbers. So the functions we looked at before, we're going to extend those to complex functions. So the previous domain was only real numbers. Now we're going to extend that domain to include complex numbers as well. Okay, so it is extensions to these existing functions. Okay, but we're going to have a look at that next time. Okay, so I'll see you then.